Radicals and rational expressions, day 2. Again, stuff that you've seen before, but just a little bit of review with it. A lot of what we're going to do today is going to be rationalizing denominators. So remember what you should have had from your Algebra 2 days is that you cannot have any sort of radical or rational exponent in the denominator spot. So whenever we do that, we have to get rid of it. So there's really two kind of thought processes to how to rationalize a denominator. One is just to automatically, like in this case, multiply, which this is really the only option you have here, but is to just whatever's in the denominator here as a square root or a rational exponent is to multiply by the same thing. So if you have a square root of 3, you're going to multiply the top and the bottom by both the square root of 3. You're not changing its value. Square root of 3 over the square root of 3 is just 1. It's just another way of looking at it. Okay? All you're really doing is taking this 1 over the square root of 3. You're not changing its value. You're just changing its look. Okay? The example I always gave my students before was like when you get out of bed in the morning, you're in your pajamas or whatever you slept in. Most likely you probably get up and you change clothes to whatever you come to school in. You didn't change, it's just the outfit or whatever did, is really the best way that I can put it. Okay? You're still you. Doesn't matter what kind of clothes you're wearing. So whenever we do, we just multiply straight across, whatever's on top, whatever's on bottom. Okay? The whole point is basically to get rid of that radical in the bottom side. So whenever we go 1 times the square root of 3, we get the square root of 3. Square root of 3 times square root of 3 is square root of 9, which is just a regular 3 underneath the radical. If we have to rationalize the denominator, if we have 15 over the square root of 6, okay, there's not really a number. Okay, I'm really looking two different ways. One way is I'm looking to find a number that I can multiply by 6 to get a perfect square. Okay, as far as perfect squares, in this case, the first one is going to be actually where they're going to match. So it's going to be the square root of 6 and the square root of 6. So, because if I multiply it by 2, it's 12. Multiply it by 3, it's 18. 4, it's 24. 5, it's 30. It's not going to get to be a perfect square until I multiply both the top and the bottom by the square root of 6. Most of the time, unless you have a radical in the numerator spot, you're really just going to take whatever number or variable that's on the top side and however you rationalize it, and you're just going to basically rewrite it straight across. Now, in some cases, similar to what we did yesterday, if there is something in a radical, then you're going to have to combine it. So then on the bottom side, I have the square root of 36. And then 15 times the square root of 6 all over 6. Now, I'm not finished in this case because I have 15 that's on the outside of the radical and I have 6 that's on the bottom side of that's not underneath the radical. So what can I do if I have 15 over 6? Can I simplify that? Yeah, what can I divide both of them by? I can divide both of them by 3. That's going to go to a 5. That's going to go to a 2. So my final answer is 5 times the square root of 6 all over 2. Now, on the one on the bottom side where it's number 10, so I have 12 divided by the square root of 8. You have really about 3 different options that you can go about this. Okay? I think regardless of what you're going to have to do, if this isn't a perfect square, you're going to have to rationalize. So the one thing I would tell you not to do, I wouldn't simplify it. Okay? Could we simplify the square root of 8? Yeah, we could go square root of 4 and square root of 2, right? We're going to simplify it and we would have 2 times the square root of 2. Okay? That doesn't get rid of anything. It still leaves a radical in there. That's just a lot of extra work that may or may not help us. Okay? It's still going to get the same answer, but that's probably not the option that I would go with. Okay? there's always the fail-safe of, well, just like there was in 9 of a square root of 6, so I'm going to multiply it by the square root of 6. We can go, down the bottom, we can go square root of 8, square root of 8. Okay? The problem with that is, like we already talked about, that square root of 8 that's on the top side, we're going to have to simplify that again. Okay? I want to do the least amount of work possible. Okay? Work smart, not hard. Okay? The first two options gave me a lot of extra work that I probably didn't have to do. Okay? What I think is the easiest way to go about this, okay, and a lot less chance of making a mistake, what is a perfect square that I can get by multiplying 8 by? What's a number that I can multiply 8 by to get a number that is a perfect square? That is 1, 4, 9, 16, 25, 2, right? To get the 16. Okay? So what I would suggest, excuse me, is to go the square root of 2 and the square root of 2. In doing that, I'm going to have 12 times the square root of 2 on top, and then I'm going to have the square root of 16 on the bottom. So 12 square root of 2 over 4. Now can I simplify this? Yep, that's going to be gone, and that's a 3. So my final answer is 3 times square root of 2. Right? So if you have your second option, so one option was to find a number that I can multiply 8 by to get a number that is a perfect square. Okay? The other way of doing this, or one of the other ways, would be just kind of your fail-safe to where I go times the square root of 8 times the square root of 8. So the top side is going to be 12 times the square root of 8, and then square root of 64, which is going to be 8, right? So I have 12 times the square root of 8 all over 8. So can the 12 and the 8 reduce? Yeah, I can divide both of them by 4, right? So then I'm going to have 3 square root of 8 over 2. Now, can I simplify the square root of 8? Yeah. Okay. I can simplify the square root of 8 because I can divide it by 4. So basically I'm going to have 3 times the square root of 4 times the square root of 2 all over 2. Well, what's the square root of 4? 2. So what's 3 times 2? 6. So I'm going to have 6 times the square root of 2 over 2. 6 and 2 can reduce to where that's a 3 and this is a 1. And I'm right back to where I ended up earlier. Okay? Both ways are right. One way, I think the way in yellow is a little bit easier if you can see it. If you can't, it's okay. We can still get there. The only thing I don't like about the way that's in the white color as opposed to the yellow is that there's a lot more opportunity to make a mistake or to not get everything simplified. Okay? The way in yellow can kind of help eliminate less mistakes, so that way we don't have that option. Now, as far as the third way, basically all that's going to happen there is let's go back to yellow. So I'm going to do it kind of up here. So 12 over the square root of 8 would be to simplify the bottom side first and have 12 over square root of 4 square root of 2, and then go 12 over 2 square root of 2. Now we can do it a couple different ways. I would just probably cancel that and make it 6 over the square root of 2. Now I can't leave a radical in the bottom side, so square root of 2, square root of 2. Hope I don't run out of room. 6 square root of 2 over 2. That's going to be 3. So again, my answer is 3 square root of 2. So I have 3 options here that I can go about. Me personally, I'm going to stick with the first one, but know that there are still other options. Okay? You still have options that you can go through if needed. A conjugate just means that we are going to have 2 terms that are we're going to have a radical. We're going to have one term that maybe one or both terms are radicals, and that there's going to be a positive and a negative version of it. Okay, so whenever we have a conjugate, okay, and whenever I say a positive and a negative, the only sign that ever changes is going to be the plus or the minus. So I'm going to have a sum and a difference of 2 terms, or that has 2 different terms that are the same terms in each part. Okay, so whenever we do this, the conjugate, the only thing that'll ever change is if I start with a subtraction problem, I'm going to turn it into an addition problem, and I'm going to multiply those 2 values together. Okay. What you're used to seeing is a difference of 2 squares, where what ends up happening is that if I multiply the square root of a times square root of a, well, that's a, okay, because it's the square root of, or square root of a squared, which the square roots and the square go away. Whenever I would, if you foiled, whenever I go outside and inside, there's going to be a positive version of the same number and a negative version of the same number that are going to cancel. That's the whole point. We want the middle to go away. All right? We want the middle to go away, and whenever we do, because we have a radical, okay, those radicals, since they're multiplied by itself, it's going to drop off. So whenever I rationalize, regardless of what it is, okay, I'm going to do one of the other. Do you want to see 11 or do you want to see 12?
11.
Okay. So if I have a radical on the bottom, again, I cannot leave a radical on the bottom side. If it's a plus, then that means, again, I need to multiply the top and the bottom by the same value. So in doing that, whenever I multiply, whatever this is down here, it's going to match, except instead of 5 plus the square root of 3, it's going to be 5 minus the square root of 3. And then it's going to be the same thing on top. Now, you can shortcut this if you want, or you can multiply it out. I guess you can go the long way, and you can FOIL this out and go 5 times 5, and then 5 times negative 3, or negative square root of 3, and then have 5 times square root of 3, and then do the 2 positive and the plus and the minus of the square root of 3. Okay? If you want to do it that way, that's fine. But realistically, it's just going to make it so much easier. What's 5 times 5? 25. Is just to shortcut it and eliminate all the headaches of making a mistake. It's automatically always going to be a minus sign. Okay? It's always going to be a subtraction problem. And then square root of 3 times the square root of 3? Square root of 9, right? So what's the square root of 9? 3. Whatever's in that radical, that's going to be your number right here. Okay? It's basically just going to drop off. Now, the top side, we actually have to do the math of 5 times 7, so 35, minus 7 times the square root of 3. Last thing, we need to simplify the bottom. So I have 35 minus 7 square root of 3 all over 22. If you can simplify anything, simplify it, but make sure you simplify everything. Okay? Before I do anything, if there's a denominator down there, and like if it was a 7, then I could reduce the 35 and the 7. But since it's a 22, or even if it was a 21, okay, I would divide everything by 7. But the way that I always tell students is don't do anything unless both parts are going away. I don't want to have two different fractions. That's just going to be really messy, and it can look kind of not well put together. Same way whenever we have radicals that aren't perfect squares. They're cubes, they're fourth roots, things like that. Again, it's really up to you what you want to do as far as simplifying it. I'm looking for values, okay, that in this case, like on 13, that are perfect cubes. So it's a whole different list. So instead of your 1, 4, 9, 16, 25, 36, so on and so forth, it goes into that next column. So it's a new column of 1, 8, 27, so on and so forth. So of those values, what number that's a perfect cube that I can divide by 24, excuse me? 8. So I'm going to break everything up the same way. I'm going to have the cube root of 8 times the cube root of 3. Cube root of 8 is 2, so it's just going to be 2 times the cube root of 3. If you can't remember right off the top of your head what your perfect cubes are or your perfect fourths, you can find a table. Just look it up. You can find the table. Same way with 14. I have a fourth root of 8 and a fourth root of 4. Now, again, there are multiple options of doing this. The way we did it yesterday is we would have put it together and had the fourth root of 32. Okay, so then I would have to go to my perfect fourths. 1, 16, 81. So which number can I divide by 32 evenly? 16, right? So fourth root of 16 times the fourth root of 2 is just going to be 2 times the fourth root of 2. Now, one way that I showed my students last year was that I can rewrite the square root of, or I can write 8 as 2 to the third. I can write 4 as 2 to the second. So if I have the fourth root of 2 to the fifth, how many groups of 2 can I have? How many groups of 4 can I have? One group of 4, right? How many's left over? 1. Okay, it's just another way of seeing it to have 2 times the fourth root of 2. Okay, if it's a perfect number, it doesn't have to be a perfect fourth. It can be a perfect cube. It can be a perfect square. Okay? And you can rewrite it different ways. So that way, if you want to do it that way, if you don't want to have to multiply things together, it just gives you other options. Okay? I'm all about options and giving you as many tools as you can get. you have to have the cube root of 2 if you want to be able to add or subtract. You can separate out the 4th root of 81 and the 4th root of 16 and go that route. Okay, both of those are perfect fourths, so that works out nicely. Okay, it doesn't change, the approach doesn't change if the problem does. Okay, it's still the same idea, it's just a little bit different set of numbers is all it is. Whenever we have a rational exponent, whatever your denominator is, that's your root. Whatever your numerator is, that's your exponent. Okay? So whatever your numerator is your exponent. Your denominator is the radical's index, or that's your root. Okay? Again, nothing new. So like if I had on 17, if I had 27 to the 2/3 power, I'm going to rewrite this as the cube root of 27 all squared. Well, is 27 a perfect cube? Yeah? 3 times 3 is 9. 9 times 3 is 27. So I can rewrite this as 3 squared. Well, what's 3 squared? Well, it's 9. Do whatever's on the inside first, and then do whatever's on the outside second. If you can simplify inside your parenthesis, do that first, and go about it that way. It doesn't change your rules. If it's negative, what do you need to do? Flip it to the bottom side. Okay, 1 over 81 to the 3/4 power, then change it over. You have the same base with, you're still going to multiply the 5 and the 7 together. You have the same base with your x's. You're just going to be able to add 1/2 plus 3/4. You're going to have to be able to add, or in this case, subtract fractions with 5/3 and 3/4. Remember, whenever you add and subtract fractions, you get the denominator the same first. All this is just asking is reducing the index of a radical. Basically, just writing it as, how would you write 22 as a rational exponent? X to what power? 3 over 9, right? What is 3 over 9? 1/3. Now, if you're going to leave it like that, that's fine. I'm okay with that. Or just go cube root of x, because that's just 1. Really, all you're doing is just seeing how we can simplify everything. Bigger number. You're just going to reduce it just like you would a fraction. None of that changes. Reminder, test, Friday. We'll go through P4, which is polynomials and multiplying and adding and subtracting and all that tomorrow. And then next week we will do P5 and then review.